well they are designed and built, and no matter how well they are maintained, machines can break down as a result of component failure. Components can fail because of excessive wear or fracture. When failure occurs, it is critically important to determine the cause of failure, discuss it with those responsible, and take appropriate corrective action. This process is called applied failure analysis. Its application can help minimize the likelihood of similar failures occurring in the future. This module focuses on failures that occur due to metal fracture and the process for identifying and analyzing those fractures. In this program, you will learn to describe loads and stresses on parts, explain why they fracture, identify the type of fracture that has occurred, trace the fracture to its initiation site, and determine why the fracture occurred. Most of the information you need is contained on this videotape. The workbook which accompanies this tape contains additional information and review questions to allow you to check your understanding of each major topic. It also contains a pre-test that will measure how much you already know about fracture analysis, and a post-test that will measure your performance after you complete the module. If you haven't already done so, stop the tape now and complete the pre-test. In order to understand how and why fractures occur, you must first be able to recognize and explain the different types of forces or loads that can cause fractures. There are 5 possible load types: tensile, compression, torsion, bending, or shear. Tensile loads are forces that try to pull something apart, much like a game of tug-of-war or stretching a rubber band. This cable is experiencing tensile loads due to the weight of the logs being drug along behind the skidder. Compression loads are just the opposite of tensile loads. They are forces that try to squeeze an object together and make it shorter, just like crushing an aluminum can underfoot. The cylinder rod on this excavator bucket experiences compression loads when hydraulic pressure pushes it on one end and the resistance of the ground pushes it on the other. Bending loads are forces that try to deflect an object while it is held at one or both ends. This motor grader frame experiences bending loads as the weight of the machine pushes down on the frame and the ground pushes up on the tires. Torsion loads are forces that try to twist an object in opposite directions. A good example is the load on a pencil as it is being sharpened. A drive shaft experiences torsion loads as the engine tries to turn it in one direction while the forces on the wheels try to prevent it from moving. Shear loads are opposing forces that try to push an object in opposite directions at the same time. An example is the loading on a piece of paper when it is cut with scissors. Shear also occurs during torsional loading and is called torsional shear. This bucket pin is experiencing shear loading by the structures it holds together. Watch the outriggers on this backhoe loader as they are lowered. Which of these 5 load types did the hydraulic cylinder experience? Did you select compression? If so, you're correct. The cylinder pushes against the outrigger on one end and against the frame on the other, resulting in compression loads. In this topic, we reviewed the 5 load types that can be applied to parts. It's time for a brief review. Stop the videotape here and complete the corresponding materials in the workbook. We are now ready to look inside various components to see what internal effects or changes are created by loads. The loads we discussed in the last topic create stresses inside parts, and as we will see, the type of load determines the type of stress that occurs. Tensile loads, that is, forces that tend to pull an object apart, result in internal tensile stresses that resist the pull and keep the part together. These internal stresses can be visualized by imaginary lines inside the part called stress lines. As applied loads increase, internal stress increases. Tensile stress lines try to distribute themselves evenly over the available cross-section of the part. In fact, the mathematical definition of stress is force divided by cross-sectional area. Compression loads, that is, forces that try to squeeze an object together, create internal compressive stresses that resist the squeeze. These internal stresses are illustrated by imaginary compressive stress lines. Compressive stress distributes itself evenly over the cross-section, just like tensile stress. Bending loads, forces that try to deflect an object, result in compressive stress on the concave side and tensile stress on the convex side. The center of the object experiences little or no stress. Lines of bending stress do not distribute themselves evenly over the cross-section of the object, but are highest at the surface and diminished toward the center. Torsional loads, forces that try to twist objects, result in internal lines of stress that spiral along the object's length. Torsional stresses are highest at the object's surface and diminish towards the center. Shear loads, forces that try to push an object in opposing directions, result in lines of stress parallel to the loads. These stress lines are highest at the loaded area and diminish with distance. Can you identify the type of load this excavator boom is experiencing and describe the internal lines of stress? If you said bending load and described the lines of stress as tension on the top side, compression on the bottom side, and zero in the middle, you have a good understanding of the type of loads and the lines of stress they generate. In this topic, we learned that each load type generates a specific stress distribution inside a part. It's time for a brief review. Stop the videotape here and complete the corresponding materials in the workbook. Now that we are familiar with stresses inside parts, we are ready to learn about stress raisers, what they are, and how they affect stress lines. A stress raiser, also called a stress concentrator, is a physical condition on or within a part that concentrates stress lines. This concentration results in higher localized stress at the stress raiser. To see this effect more clearly, consider the stress lines in a part experiencing tensile loading. Now we will produce a stress raiser by putting a notch in the part. Notice that the lines of stress follow the new contour and are forced closer together, increasing stress at the bottom of the notch. When this condition is severe, it can cause cracks to start. The amount of stress increase that occurs depends on the sharpness of the stress raiser. Gradual contour changes increase stress slightly, while abrupt contour changes increase stress significantly. A crack has the sharpest, most abrupt contour change possible, making it the most severe stress raiser. Which of these three parts has the least significant stress raiser? The bolt, the valve, or the turbocharger shaft? If you said the valve, you're right. Since the contour change is gradual, it would have the least effect on stress. Both the bolt and shaft contain abrupt contour changes. Threads, underhead fillet, and shaft diameter change. Now that we know what stress raisers are, we need to understand where they come from. Stress raisers can be introduced through material flaws, by manufacturing errors, by design shape, and by surface damage. Material-related stress raisers, especially in steel, are usually inclusions. Inclusions are impurities remaining in the metal after the refining process. Manufacturing processes such as casting, rolling, forging, and heat treating can introduce cracks within the metal. Castings may contain voids due to shrinkage of the metal as it cools and becomes solid. Rolling or forging may fold material in on itself, creating a rolling seam or a forging lap. Sometimes it is necessary to design in abrupt contour changes, such as snap ring grooves, shoulders, small fillets, and holes. Designers plan for these contour changes and specify stronger materials or heat treatment to give the part adequate strength at these locations. Even so, these contour changes are still stress raisers that can start fractures. Can you identify any stress raisers on this connecting rod? Did you notice the contour change at the bolt seat and recognize it as a stress raiser? So far in this course, we have reviewed the 5 load types, resulting internal stresses and their distribution, and what stress raisers are and where they come from. It's time for a brief review. Stop the videotape here and complete the corresponding materials in the workbook. The speed with which loading is applied has a great effect on part response and fracture type. There are three basic rates at which loads can be applied: shock load rate, overload rate, and cyclic load rate. Shock load rates are extremely fast single-load applications. These loads can be applied in a fraction of a second, and if severe enough, can cause the part to fracture. The shape of parts that fail due to shock load generally remains unchanged. Overload rates are similar to shock load rates in that they are a single application of a high load. However, the load is applied somewhat more slowly. During overloading, the part has time to change shape, often becoming stretched or bent before fracturing. Cyclic load rates can be fast or slow and are repeated over and over, but no single load cycle is great enough to cause fracture. The combined effect of thousands or millions of load cycles can produce slow-growing cracks and ultimate fracture of the part. Cracks caused by cyclic loading generally start at a stress raiser. Under normal operating conditions, which of the three load rates is the crankshaft in this engine experiencing? If you said cyclic load rate, you are correct. Over the life of this engine, the crankshaft will experience millions of load cycles. What load type is the crankshaft experiencing? Since the crankshaft is being twisted by the pistons and drivetrain, it is experiencing torsional loads. The pistons are also applying bending loads each time combustion occurs. This completes the first lesson in the fracture analysis module. You should now be able to identify and describe the 5 different types of loads and the stress line distribution each load produces. You know what stress raisers are and how they affect stress distribution, and you should be able to identify and describe the 3 load rates. It's now time for a progress check. Stop the videotape here and complete the section of the workbook marked Lesson 1. In Lesson 1, we reviewed load types, stress distribution, stress raisers, and load rates. In this lesson, we'll discuss conditions that cause parts to fracture. We will discuss 3 general conditions that cause fractures: overloading a good part, normal loading with abnormal stress raisers present, normal loading of a weak part. In this lesson, we will learn to recognize the differences between normal and abnormal conditions. Parts often fracture because applied loads are greater than the part can carry. With severe overloads or shock loads, fracture sometimes occurs during a single load application. These fractures are referred to as ductile or brittle fractures. Other times, the overload is cyclic, and fracture occurs after many repeated load applications, as is the case with this paperclip. These types of fractures are referred to as fatigue fractures, since the metal appears to tire after many load cycles. Engineers may run a series of tests to determine the load amounts and number of cycles a part can withstand without fracturing. This is known as fatigue limit testing. Test results are often depicted on charts like this. The vertical axis represents the amount of load, and the horizontal axis represents the number of cycles applied, or part life. If we plot the cycles to fracture at various loads, we obtain the load life curve for the part. The fatigue limit is the load at which the curve becomes horizontal. Theoretically, if cyclic loading is kept below this fatigue limit, fracture should not occur. But some working conditions may vary from design expectations. Therefore, applied loads must be less than the fatigue limit. The comparison of fatigue limit to the applied load is called the design safety factor. If the fatigue limit is twice the applied load, the safety factor is 2. Any loading above the intended design load is a cyclic overload. When extra load is applied or a machine is used improperly, components may experience cyclic overloads, as shown in yellow. If cyclic overloading exceeds the fatigue limit, as shown in red, fatigue fracture usually occurs. The greater the cyclic overload, the sooner cracks start. Is this statement true or false? Parts that carry loads falling within the green area are said to be carrying normal cyclic loads, while parts that carry loads falling within the yellow and red areas are experiencing cyclic overloads. You should have said true. Any cyclic loads above the green area are classified as cyclic overloads. However, since the yellow area represents a factor of safety, parts loaded in this region are less likely to fracture than those parts experiencing loads in the red zone. Based on the graph shown here, would you say this component has a safety factor of 2 or a safety factor of 4? The correct answer is 4. Notice that the green portion of the graph is approximately 1/4 the size of the yellow area. In this topic, you learned about overloads, fatigue limits, and safety factors. It's time for a brief review. Stop the videotape here and complete the corresponding materials in the workbook. Earlier in the course, you learned about stress raisers, what they are and how they are created. Normal stress raisers, such as material flaws, holes, and fillets, are usually not a problem because they're taken into account by designers. Some abnormal stress raisers can be tolerated in parts since there is a safety factor. Severe abnormal stress raisers multiply the effect of normal cyclic loads above the fatigue limit, which can lead to fracture. Severe stress raisers include heat treat cracks, inadequate fillet radii, gouges, dents, and shrinkage voids. The design drawing for this part specifies a fillet with a radius of 120 thousandths. The actual radius measured on the part, however, is 36 thousandths. Is this an abnormal stress raiser? Did you answer yes? If so, you're right. The smaller radius results in an abrupt contour change, which increases the stress multiplication. In this topic, you learned the difference between normal and abnormal stress raisers and their effect on part life. It's time for a brief review. Stop the videotape here and complete the corresponding materials in the workbook. Sometimes the loading on a part and its stress raisers are normal, but material strength is low. When material strength is low, the fatigue limit drops. The safety factor is reduced or lost completely, and fracture can result. This can happen if the wrong material is specified, or if an incorrect manufacturing process is used to make the part. Material strength can also be affected after the component is put into service. Excessively high operating temperatures, for example, cause this bolt to weaken, leading to fracture. From their appearance, which of these connecting rods do you think still has adequate material strength to do its job? The tempered colors on the rod in the foreground indicate it's been too hot, and you correctly selected the other one. We should always be suspicious of parts that show evidence of having been too hot. During this lesson, you have learned 3 conditions that can cause parts to fracture. You learned that overloads can be applied once, causing ductile or brittle fractures, or they can be applied cyclically, causing fatigue fractures. You also learned that abnormal stress raisers or low-strength material can produce fractures under normal loading conditions. This completes the second lesson on conditions that cause fracture. It's time now for a progress check. Stop the videotape here and complete the section of the workbook marked Lesson 2. In Lesson 2, you learned how overloads, stress raisers, and material flaws can produce different types of fractures. In this lesson, you will learn how to identify the different fracture types by careful visual examination. There are a few general guidelines that are useful for identifying fractures. We can identify most fractures by making careful observations of the texture, color, reflectivity, and unique surface features. The texture or roughness of a fracture will be determined by how fast the crack grows. Faster-growing cracks produce rougher surfaces. Slower-growing cracks produce smoother surfaces. Fractures in softer metals develop more identifying surface features than fractures in harder metals. While attempting to identify fractures, keep in mind that more than one fracture type is usually present on a fractured surface, and fractures often do not contain all of the identifying features every time. Nevertheless, by applying the rules you learn in this lesson, you will be able to correctly identify fractures. Once you correctly identify a fracture, you can determine which load type and rate produced it, and whether or not the fracture was closely associated with the root cause of failure. There are three basic types of fractures: brittle, ductile, and fatigue. To understand the differences between them, you must first know a little about the internal grain structure of metal. It is helpful to compare grain structure to a stone wall held together by mortar. The metal grains can be thought of as stones, and the boundaries between the grains as the mortar joints. When fracture occurs, the grain structure comes apart, and each type of fracture separates the grains in a particular, identifiable way. Let's begin with brittle fractures. Brittle fractures are usually the result of a sudden impact load. Fracture occurs instantly, and there is little deformation. That is, the part doesn't change shape. If the two mating parts were placed together, the part would look largely undamaged. Brittle fractures can be further divided into two types: cleavage and intergranular. Cleavage fractures tend to split the grains, leaving flat surfaces. This would be similar to breaking the stones in the stone wall. Cleavage fractures usually have a rough texture with a medium gray coloration. In harder metals, the surface may sparkle, as though it contains diamonds. This effect is produced by light reflecting from the flat surfaces of the fractured grains. This valve head fracture has a rough texture, gray color, and hardly any plastic deformation. It also sparkles with different lighting angles, all characteristics of cleavage fracture. In softer metals, a surface feature called chevrons may develop. These are ridges on the fracture which usually spread out as the crack grows. This gear tooth fracture has a very rough texture, gray color, and chevrons, all characteristics of a cleavage fracture. This cylinder rod cleavage fracture exhibits a rough surface, gray color, and very distinct chevrons. After cleaning the surface and looking at it with magnification, we notice it even sparkles a little. Intergranular brittle fractures tend to break the bond between the grains, exposing the irregular shaped grain surfaces. This is similar to cracking the stone wall at the mortar joints. Intergranular fractures have most of the same characteristics as cleavage fractures. The main difference is intergranular fractures don't sparkle nearly as much as cleavage fractures. Looking closely at this fractured bolt, we see a rough surface, gray color, very little plastic deformation, and almost no sparkle. These facts tell us that this is primarily brittle intergranular fracture. This valve stem fracture is rough, has a gray color, does not sparkle, and shows no deformation. Under higher magnification, we can see how this fracture has followed the grain boundaries, exposing irregular grain surfaces. These irregular surfaces do not reflect light or sparkle, telling us this is an intergranular brittle fracture. We have just observed that cleavage fractures sparkle, while intergranular brittle fractures don't. If a lot of sparkle is present, the fracture is likely to be cleavage. But if little sparkle is observed, the fracture is likely to be intergranular. Is this fracture a cleavage fracture or an intergranular fracture? Did you recognize the rough texture, medium gray color, and sparkle? This is clear evidence of cleavage fracture. You have now learned to identify the two types of brittle fracture, intergranular and cleavage fractures. It's time for a brief review. Stop the videotape here and complete the corresponding materials in the workbook. In this topic, you will learn to identify ductile fractures and the loads that produce them. Ductile fractures occur somewhat slower than brittle fractures and are usually the result of a single overload. Consequently, the metal grains tend to stretch or change shape before pulling apart. Although ductile fractures occur more slowly than brittle fractures, the crack still travels fast enough to produce a rough surface texture. The rough surface produced by tearing the grains tends to scatter light rather than reflect it. Consequently, ductile fractures often have a dark color. A major identifying surface feature is the plastic deformation, or permanent change in shape. This deformation may be necking, bending, stretching, or twisting. Putting these pieces back together would reveal a permanent change in the shape of the metal. This is called plastic deformation. Another major identifying feature is the shear lip. Most ductile fractures start inside, where metal grains start to pull away from inclusions, creating voids inside the part. As loading continues, the grains tear apart and the internal voids grow until the only unfractured metal remaining is around the outer edge of the part. But this metal soon becomes overloaded and shears off, producing a shear lip. So the primary identifying characteristics of ductile fractures are rough surface, dark gray to black color, plastic deformation, and shear lips. These surface features will vary according to loading. Ductile fractures that are caused by tensile overloads produce rough, dark gray or black fractures with necking and a shear lip nearly all the way around the circumference. This cylinder bolt is an example of ductile fracture caused by tensile overload. Notice the rough texture, dark gray color, lack of reflection, necking, and shear lip. Under low magnification, we can see that the grains have stretched, pulling up into rows of peaks called tear ridges. It is these tear ridges that produce the dark gray color, as light is trapped in the valleys between them. A less common form of ductile fracture produces tear ridges that run radially from the center of the part to the outside. Again, the texture is rough and the color dark gray. Also, extensive necking has occurred, identifying this as a ductile fracture. When overloaded in bending, ductile fractures produce rough, dark gray surfaces. The shear lip usually occurs on the compression side of the fracture and is the last metal to tear apart. Not all ductile fractures produce a rough surface. Under shear loading, parts fracture by sliding past each other. This produces a fairly smooth texture, best described as satiny or smooth and silky. Ductile fractures produced by torsional loads can occur in either the transverse or longitudinal shear plane. If fracture occurs across the part, it is called transverse shear. Much of the fracture face is smooth and silky. At the final fracture, the surface is rough and dark gray. Final fracture often occurs near the center of the part. If fracture occurs along the part's length, it is called longitudinal shear. Grain flow can be exposed, producing a woody gray surface. How many surface features can you identify that characterize this as a ductile fracture? If you listed rough surface, dark gray color, plastic deformation, and a shear lip on one side, you've done an excellent job of visual inspection. Can you identify the type of load that produced the fracture? The correct answer is tensile loading. Did you get it right? In this topic, you learned the characteristics of ductile fractures and the types of load that caused them. It's time for a brief review. Stop the videotape here and complete the corresponding materials in the workbook. Now let's turn to the third major type of fracture and learn what surface features we can use to identify fatigue fractures. There are two categories of fatigue fractures, high cycle and low cycle. While each has similarities, they are different enough to allow you to tell them apart. Let's learn to identify high cycle fatigue fractures first. High cycle fatigue fractures occur after hundreds of thousands or millions of load applications. A tiny crack begins in the part, perhaps at an inclusion or some other stress raiser, and grows slowly with each cycle. As the crack grows, it picks up speed. At some point, the remaining unfractured area becomes overloaded and brittle or ductile fracture occurs. This is called final fracture. Since high cycle fatigue occurs very slowly, the surface texture is quite smooth. The color is a light silver gray in steels, since the fracture is smooth enough to be reflective. Prominent surface features called beach marks and ratchet marks are often found on fatigue fractures. The location where the crack starts is called the initiation site. A beach mark is formed when a fatigue crack changes speed. If there is no change in speed, beach marks will not be seen. Also, beach marks may not form in hard materials. Ratchet marks may or may not be present on a fatigue fracture. They indicate high stress and multiple initiation sites. That is, several fatigue cracks may have started at nearly the same time and near the same location, but on different planes. As the fatigue crack grows, the individual fractures may join together and form one large crack. The ledge between the cracks is called a ratchet mark. This fracture exhibits beach marks, ratchet marks, and a final fracture that is ductile. The texture is smooth and silver gray in color. This is a fatigue fracture with more than one initiation site. The size of the final fracture is an indication of the severity of the applied load. Large final fractures generally indicate large loads, while smaller final fractures indicate lower loads. Fatigue crack surface features depend on load type. Tensile fatigue produces beach marks that are circular and concentric to the circumference. These fractures may initiate on the outside with final fracture beneath the surface, or they may start beneath the surface and grow outward. Bending fatigue produces beach marks that start at one location and spread outward towards the other side of the part, like ripples on water. Reverse bending can start two fatigue fractures, one on each side of the part, with beach marks running towards each other. Final fracture occurs between the cracks. Rotating bending produces beach marks that grow inward from the circumference. Final fracture occurs in the center region. Torsional fatigue cracks often leave distinct beach marks and progress at 45-degree angles within a part. Reverse torsional fatigue can produce a starburst fracture like this, or an X-shaped crack. The fracture first grows in one direction and then the other as the load reverses direction. Fatigue fractures produced by longitudinal shear loads usually grow along the grain flow, leaving a somewhat woody appearance. Occasionally, a fatigue crack will break up into several smaller cracks in the middle of the fracture due to changes in part geometry or increased stress. If these cracks recombine into a single crack, a series of ratchet marks may be formed. It is not critical that you remember all the different beach mark patterns and the loads that cause them. The purpose of these examples is to help you recognize the characteristics of high-cycle fatigue fractures. Low-cycle fatigue occurs much faster than high-cycle fatigue, taking fewer cycles to reach final fracture. Since the crack propagates faster, the surface texture is rougher on low-cycle fatigue fractures. The color is a darker gray, reflecting less light, and the beach marks are more widely spaced and easier to see. This type of fracture is usually caused by severe cyclic overloading, and we should expect the final fracture size to increase. Notice the rough texture, prominent beach marks, ratchet marks, and a large final fracture. All these facts indicate low-cycle fatigue. Please list the characteristics of this fracture and identify it as either high-cycle or low-cycle fatigue. Our list of characteristics should include smooth texture, silver gray color, closely spaced beach marks, and small final fracture, characteristics of high-cycle fatigue. Compare these two parts. Which is high-cycle fatigue and which is low-cycle fatigue? The one on the left is low-cycle fatigue because it has several rough textured fatigue cracks starting on the top and right-hand sides and also has a large ductile final fracture. The one on the right is high-cycle fatigue because it is smooth with closely spaced beach marks and a small final fracture. During this lesson, you have learned the three basic types of fractures and the loading that produces them. You learned how to identify cleavage and intergranular brittle fractures, ductile fractures, and high and low-cycle fatigue fractures. And you learned the various types of surface features produced by different loads. This completes the video portion of fracture identification. Stop the videotape now and complete the section of the workbook marked Lesson 3. Now that we can identify the various fracture types, we will learn to determine where cracking started. This is called locating the fracture initiation site. It is important to find the initiation site because it can reveal the reason why cracking started, regardless of fracture type. As you recall, there are two types of brittle fractures, cleavage and intergranular. First, let's learn to find the initiation site of a cleavage fracture. Quite often, cleavage fractures in softer metals produce chevrons, one of the surface characteristics we learned in Lesson 3. Chevrons are often shaped like arrows, pointing to the initiation site, or they may look like a handprint that converges at the initiation site. This piston skirt has a brittle fracture with chevrons. The chevrons form a handprint pattern. They converge at the bottom, indicating this is the initiation site. We should examine this area carefully for stress razors or other clues that explain why cracking started. Chevrons are present on this fractured gear tooth. We can see they come together at the bottom edge, indicating brittle fracture started there. We should inspect this initiation site for other clues that might reveal why the crack started. Chevrons on this fracture form arrows pointing toward the initiation site. This fracture appears to have started at bottom center of the screen. In softer metals, brittle fracture usually produces these chevrons, while in harder metals, brittle fracture usually produces a sparkly, crystalline appearance without chevrons. It is much more difficult to locate the initiation sites of sparkly fractures since there are no chevrons to guide us. Sometimes the initiation site can be located by looking for surface damage, such as a nick or dent where an impact load was applied. Frequently, the fracture changes from brittle to ductile and leaves a shear lip at the final fracture. We should then suspect the initiation site is opposite the final fracture. Sometimes there are no chevrons or impact damage to guide us to the initiation site, and we have to examine other parts for clues or road signs to help us understand what happened. We should also remember that most cleavage fractures are a result of another problem and are not the root cause of failure. Finding the initiation site of an intergranular brittle fracture is often very difficult. Sometimes a faint chevron pattern is present and points to the initiation site. Or we may find a corrosion pit, which also identifies an initiation site. But other times there is no evidence on the fracture to locate where cracking started, and we have to rely on facts gathered from other parts. We've just reviewed ways to find initiation sites of brittle fractures. It's time for a brief review. Stop the videotape here and complete the corresponding materials in the workbook. Now let's learn how to do the same thing with ductile fractures. The location of a ductile fracture's initiation site depends on the type of load that was applied. Tensile loads pull grains into longer, thinner shapes and eventually tear them apart, leaving a mountain peak valley appearance. Cracking usually starts near the center and spreads to the outside where stretching and necking are occurring. The outside surface holds together longer, then fractures in shear, producing a shear lip around the outside. Therefore, the location of the initiation site for ductile fractures produced by tensile loading is in the general vicinity of the center of the part. Compressive fractures due to overload are extremely rare. In hard metals, they cause fracture, while in soft metals, they result in yielding. Bending loads tear grains on the side experiencing the greatest tensile stress. The crack grows through the cross-section until the remaining metal shears, forming a shear lip at the final fracture. Torsion can produce either a transverse shear or longitudinal shear fracture. Transverse shear fractures start by tearing the grains around the circumference, where shear stress is the highest. Cracks then progress inward, and final fracture is toward the center. The fracture faces usually slide against each other and smear the fracture detail. Longitudinal shear fractures caused by torsion also start on the surface where shear stresses are highest and grow lengthwise and inward along the part, tearing grains along the way. If a part is subjected to a direct shear load, The fracture starts across the entire surface at the same time. As the fracture surfaces slide against each other, they wipe out the fracture detail, leaving a smooth, silky appearance. Can you determine the kind of load that broke this shaft, the type of fracture present, and its initiation site? If you said torsional loading produced a transverse shear fracture with the initiation site around the outside surface, you're correct. As we have seen, ductile fracture initiation sites are usually general areas rather than specific points. Fortunately, these initiation sites are seldom of importance in finding the root cause of failures. It's time for a brief review. Stop the videotape here and complete the corresponding materials in the workbook. Initiation sites of fatigue fractures can be very helpful since they often start at abnormal stress risers, and they are the easiest initiation sites to locate. Beach marks, ratchet marks, and final fracture locations all help us determine where a fatigue crack starts. Beach marks, which are found on many fatigue fractures, are an excellent guide to fracture initiation sites. The beach mark pattern varies depending on the type of load, but is usually more closely spaced at an initiation site and more widely spaced near the final fracture. As you recall from Lesson 3, this beach mark pattern is typical of bending fatigue. The initiation site is easy to locate since the beach marks are more closely spaced and appear to radiate away from it. When an initiation site isn't obvious, it is possible to eliminate where it can't be. Exclude areas where the crack could not possibly have started, such as the final fracture area. With bending fatigue, the initiation site often lies directly opposite the final fracture. We see beach marks and ratchet marks on the right and left side of this reverse bending fatigue fracture. Ratchet marks are another surface characteristic useful for identifying initiation sites. Sometimes the ratchet marks are more obvious than beach marks, as in this case. These ratchet marks indicate two initiation sites, opposite each other. Beach mark patterns on rotating bending fatigue fractures can be confusing, since they often surround the final fracture, giving the appearance that it is the initiation site. Notice that the beach marks are more widely spaced and distinct near the final fracture. Careful examination with different lighting angles reveals that the beach marks actually start at the lower left, nearly opposite the final fracture, and that the curve of the beach marks reverses due to the high stress at the part's surface and low stress inside. Fatigue cracks start where ratchet marks and beach marks start. Just above center, we see a distinct line where ratchet marks and beach marks begin. This tells us the initiation site is not at the surface, but deep inside the part. Ratchet marks like these that start at the surface indicate fatigue cracking initiated on several different levels along the lower edge. Can you identify what type of fracture this is and where it started? If you said it is a brittle cleavage fracture with chevrons that point to the lower edge as the initiation site, you are absolutely correct. Can you identify this fracture and locate its initiation site? If you saw plastic deformation, shear lips, and a rough woody center, you probably called this a ductile fracture with an initiation site somewhere near the center. Try identifying this fracture and tracing it to its starting point. The beach marks on this fatigue fracture indicate it started at the lower right with final fracture at upper left. Can you locate the initiation site on this fracture? Is it surface or subsurface? You should have noticed that ratchet marks and beach marks started inside the crankshaft. Therefore, the initiation site is subsurface. In this lesson, you have learned to identify initiation sites of brittle, ductile, and fatigue fractures by using fracture surface features. We know that the initiation sites on brittle and ductile fractures are usually not as important as initiation sites on fatigue fractures since fatigue fractures are often closely associated with the root cause of failure. This completes Lesson 4, Locating Fracture Initiation Sites. It's time now for a progress check. Stop the videotape here and complete the section of the workbook marked Lesson 4. Once we locate the fracture initiation site, we are nearing our objective to determine why the fracture occurred. In this lesson, you'll learn to recognize whether a fracture occurred due to an abnormal stress razor, cyclic overload, low material strength, or damage resulting from abusing the equipment or from another part that has already failed. Let's look first at abnormal stress razors. Abnormal stress razors include material problems, process cracks, incorrect geometry, handling damage such as nicks or dents, or cuts and gouges created during maintenance or operation. Material problems such as inclusions and shrinkage voids are usually internal, meaning initiation sites can be subsurface. Inclusion shape may be spherical or long and thin like pencil lead. Shrinkage voids are irregularly shaped cavities. Inclusions can start fatigue cracks inside the part. If a crack starts from a spherical inclusion or across a long, thin inclusion, it can produce a bullseye appearance. The crack grows very slowly away from the inclusion, creating a target-like appearance with the inclusion at the bullseye. If cracking starts along an inclusion's length, instead of a bullseye, we'll see a normal fatigue appearance. Shrinkage cavities are another type of internal problem that can cause fatigue cracks to grow outward toward the part's surface. Some shrinkage cavities can be identified by dendrites. Dendrites are the long rows of spherical metal grains seen here. Large shrinkage cavities can weaken a part enough for normal loads to cause fracture. Before deciding if failure is due to a material problem, we should verify that loading was not excessive, because excessive loads can start fractures at normal size inclusions. If surface cracks are created during metal forming, heat treating, or processing, they are called pre-cracks and act as severe stress razors when the part is loaded. Most pre-cracks are ductile or brittle and can be recognized by their different surface texture. Fatigue cracks with beach marks and ratchet marks may begin at the bottom of the pre-crack. Pre-cracks can sometimes be identified by dark forging scale or temper oxides inside the crack. This indicates the crack existed during heat treat, a possible forging lap or quench crack. Sometimes a pre-crack has paint, rust, or oxides on its surface, good evidence that the crack existed before the part was placed in service. For example, the pre-crack in this part has a dark stain, suggesting it occurred during manufacturing. Ratchet marks and beach marks start at the bottom of the stained area. Contour changes are another form of stress razors. Holes, keyways, fillets, and grooves are examples. If dimensional accuracy is not maintained, contour changes can become too abrupt, resulting in an abnormal stress razor. If we suspect a contour problem, we should compare the part with a new one, a good used one, or take measurements to verify dimensions. A fillet on this connecting rod was machined too sharply, creating an undersized radius, an abnormal stress razor. During normal cyclic loading, a fatigue fracture started at this location. Notice that beach marks lead us to the surface, not to a pre-crack or inclusion. Another source of stress razors is surface damage. Improper assembly practice, rough parts handling, wear, corrosion, etc. can create this damage. We may need to compare failed parts to good parts to determine if an abnormal surface condition exists. The connecting rod parting face on the top is normal. The one on the bottom has fretting corrosion, an abnormal stress razor. This bolt contains a fatigue fracture. The beach marks lead us to the initiation site, which shows no bullseye, pre-crack, or contour change. A closer look reveals a dent at the origin. This surface damage caused the failure. We now need to discover how the dent got there. Can you trace this fracture to its initiation site and determine if an abnormal stress razor started it? You probably noticed beach marks and ratchet marks starting at a distinct subsurface line. This part of the fracture has a different texture. This rougher texture is actually a ductile or brittle pre-crack, an abnormal stress razor that started the fracture. See if you can trace this fracture to its initiation site. What do you see there? You should have identified a bullseye just to the right of a dent at the bottom of the fracture. In this topic, you learn to recognize fractures caused by abnormal stress razors. It's time for a brief review. Stop the videotape here and complete the corresponding materials in the workbook. If careful examination of a fatigue initiation site shows no evidence of abnormal stress razors, we should next look for road signs of cyclic overload. Indications of cyclic overload are multiple initiation sites, large final fracture, and low cycle fatigue. Cyclic overloads often start several fatigue cracks at the same time. The fracture often connects ratchet marks as an indication of excessive cyclic loading. The bolt on the right has a much larger final fracture than the bolt on the left, suggesting it experienced excessive cyclic loading. The fatigue crack didn't have to progress nearly as far before the remaining metal was overloaded and failed. Another good indicator of excessive cyclic loading is low cycle fatigue. Low cycle fatigue produces rougher, darker fatigue surfaces with prominent, wide-spaced beach marks and larger final fractures. Which of these two fractures do you think experienced excessive cyclic loading? If you said the one on the left, you're correct, because it is the one with the rougher surface, more widely spaced beach marks, and larger final fracture. This topic discussed fractures caused by cyclic overload. It's time for a brief review. Stop the videotape here and complete the corresponding materials in the workbook. Sometimes low material strength causes fracture. If careful examination of the fracture reveals no abnormal stress razors or excessive cyclic loading, then we should look for evidence of low material strength. There are several indicators we can use to help identify low material strength: temper colors, excessive plastic deformation, identification marks, and case depth. Temper colors on steel are the result of excessive heat and oxidation. Colors such as these mean this part was exposed to temperatures in excess of 500 degrees Fahrenheit. As temperatures increase above 1,000 degrees Fahrenheit, temper colors become black and heavy surface oxides form. Excessive plastic deformation or melting is another good indicator a part has experienced high enough temperatures to lose strength. Sometimes low-strength parts can be identified by markings. Bolts, for example, often have identification marks that indicate their relative strength. The left bolt with more radial lines indicates higher strength than the bolt on the right. A part may have low material strength because of improper case depth. Case depth should be observable on fractures, so if we don't see it, we should gather more facts in this area. Identify which indicator of low material strength is present on this part. Why does this indicate low strength? You should have recognized temper colors which indicate the part was heated above 500 degrees Fahrenheit. These temperatures can destroy heat treatment and reduce part strength. Our discussion to this point has focused on fatigue fractures which are frequently associated with the root cause of failure. Stop the videotape here and complete the corresponding materials in the workbook. We now need to discuss brittle and ductile fractures, which are usually resultant damage. If we have all the failed parts and only brittle and ductile fractures are present, there are three possibilities. First, improper operation, which can produce shock loads or overloads strong enough to fracture the parts. Second, a large abnormal stress raiser, which can weaken the part enough to cause failure during normal loading. And third, parts with low strength, which can stretch, deform, and fracture with normal loading. This bolt was the only fractured part obtained from a failure. What road signs do you see? What type of fracture is it? And why did it start? If you observed a rough fracture surface, plastic deformation, and shear lips, you correctly identified this as a ductile fracture. You probably could not find an initiation site, so a large abnormal stress raiser is ruled out. Assume the bolt had the correct head markings. Also, there are no temper colors. These facts indicate the material was the right strength and was not weakened by excessive heat. These observations tell us the fracture was probably due to an overload condition, and the bolt fracture is resultant damage. We should look at the related parts to determine how the overload occurred. During this lesson, you've learned how to determine if fractures were caused by an abnormal stress raiser, cyclic overloading, low material strength, or for some other reason such as improper operating conditions. This completes the fifth and last lesson in this course on fracture analysis. We hope you've enjoyed it and can profit from it by applying these skills to your daily work experiences. To check your understanding further, stop the videotape here and complete the section of the workbook marked Lesson 5.